We're going to continue our discussion of probability by doing some examples with the normal distribution and introducing you to the idea of the normal table and how you can utilize it. So first of all, I want to pull up the normal table and show you what it looks like. Back out and give you a bigger version of it here. The normal table in the back of your textbook or online for your textbook has 2 pages to it. One where it deals with the positive z-scores and one where it deals with the negative z-scores. In both cases, it has a picture at the top that shows you a shaded region. The values in the body of the table represent the area of those shaded regions. So the body of the table is the probability of lying left or being less than the particular value of z. For example, let's blow it back up a little bit here. If I were to look at this 0.5910, 0.5910, that would be the area under the curve to the left of z equals 0.23. Or in other words, we would have a 59.1% chance of having a z value less than 0.23. So when we want to read something off the table, we're going to look down the left-hand column to get the integer and the tenths digit. We're going to read across the top to get the hundredths digit, and we're going to see where a row and a column intersect to get the value from the table. So let's take some examples. The first one we're going to look at is the probability that z is less than 0.68. So to come up with a probability that z is less than 0.68, I'm going to go to my normal table. I'm going to go to the 0.6 row and the 0.08 column, and where those two things intersect, this 0.7517, that is the probability that I'm looking for. Right? This is the amount of area that lies to the left of 0.68. So if we go back over, it's 0.7517. Okay. See if you can find the probability of coming up with z equals, or z being less than 1.82. Again, we'll go back to our table and stop for a second and see if you can find the probability of being less than 1.82. In order to calculate that, we would do the 1.8 row and the 0.02 column, and we see 0.9656. So our probability of being less than 1.82 is 0.9656. What about being less than minus 1.47? It's the same process, but we'll have to use the other page of the table. We'll go to minus 1.4 row. We'll go to the 0.07 column, and we will see 0.0708. So the probability of lying to the left of minus 1.47 is 0.0708. So anytime I have a less than, I'm just going to read it directly off the table. Okay, now we're going to go on to some examples of greater than. With greater than, we have a little more difficulty, but not too much more. Know that we have a normal or a bell-shaped curve, and that's not a very good bell-shaped curve, but we'll deal with it. And here's 0. If I look at 1.26, the table gives me that value. So this comes from the table. Equals the probability that z is less than 1.26. But I want this part here. This is the probability that z is bigger than 1.26. So note that that is the opposite of what comes from the table. How can we use the table then? Well, we know that the total area under this curve is 1. So we know that the probability of being bigger than 1.26 is the same thing as 1 minus the probability of being less. That is 1 minus the probability of being less than 1.26. So we'll look on our table for 1.26. So we'll go to the positive side and we'll look up 1.26. So we'll go to the 1.2 row. We'll go to the 0.06 column, and we see 0.8962. So that gives me then a value of 1 minus 0.8962, which is 0.1038. So let's take another example like that. Let's do the probability that z is bigger than minus 2.05. Again, in a similar fashion, the table is going to give us minus 2.05. The table value comes from here, so this comes from the table. We want this area, though, because we want the value bigger than minus 2.05. So we know that that's 1 minus the probability that z is less than minus 2.05. So we can go to our normal table. We'll go to the negative side of it. We'll look up in the minus 2 row. And the 0.05 column. And we get 0.0202, so this is 1 minus 0.0202, which is 0.9798. So we end up with, again, one minus 0.0202, which is 0.9798. Okay. One thing to note here that, so first of all, the probability that z is less than a is 1 minus the probability that z is, or excuse me, the probability of being bigger than a is 1 minus the probability of being less than a. But you may also notice on the diagram, because this is symmetric, the probability of being bigger than a is the same thing as the probability of being less than the opposite of a. So in other words, if I were to go to, for this example, and I look at minus 2.05, the probability of being bigger than minus 2.05 is the same thing as the probability of being less than positive 2.05. So I can go to my table and I can read it off, and if I look at positive 2.05, you can see the 9798 right there. I prefer to use the complement part of it that we used in here. So I prefer to use the 1 minus p of z less than a. But you can take advantage of the symmetric aspect of it if you wish. So now let's look at some problems with in between. Well, going in between, notice that would be 0.54 and 1.75. I want the area between those two. Well, in terms of my table, that would be the area all the way to the left of 1.75 minus the area less than 0.54. So this is really the probability that z is less than 1.75 minus the probability that z is less than 0.54. Again, we get the probability of being between two numbers by taking the probability of being less than the bigger one minus left of the smaller one. So we're going to go to our normal table and we'll look up 1.75. So we will go to our 1.7 row and our 0.05 column, and that gives me 0.9599. And from there, we will subtract off the value less than 0.54. So I'll go to my 0.5 column row and my 0.04 column, which is 0.7054. So when we go to calculate it, it's the probability of being less than 1.75, which was 0.9599, minus the probability of being less than 0.54, which was 0.7054, which then gives me 0.2545. So let's take another example like that. Being between minus 1.08 and 1.13. Again, because I'm looking between two, I'm going to take the probability of being less than the bigger one minus being less the smaller one. So I would go to my table. I'll look up 1.13 gives me 0.8708. And then I will go to the negative part of the table. And I will look up minus 1.08. So minus 1.08. And I get 0.1401. So I end up with 0.8708 minus 0.1401, which is 0.7307. And in a similar fashion, to get between minus 2.17 and minus 0.46, I'm going to get the probability of z being less than minus 0.46 minus the probability that z is less than minus 2.17. We can go to our table, and we have minus 0.4. Is it doing that? It's not letting me pull that back up. So hold on just a second. There we go. Now we'll draw on it. So I go to minus 0.4, 6, which is 0.3228, minus what happens when I put in negative 2.17. So we're going to go to minus 2.1, 7, and that's 0.015. So this gives me 0.3 1.078. Again, hopefully I did my arithmetic correctly there. So we'll again go take 0.3228 minus 0.0150, which gives me 0.3078. Okay. So for doing less than, I'll read directly off the table. If it's greater than, I'll take it off the table and take that value away from 1. If it's between two numbers, I do the bigger one minus the smaller one. Or find the bigger one in the table, subtract off the smaller one from the table. What happens, though, if I have something where it's not just z, and I have something like a mean of 20 and a standard deviation of 3? Well, this is where the z-score comes in. What we're going to do is we're going to translate this into something that can be found in the table by taking the observed value minus the mean over the standard deviation. It gives me the probability that z is less than 1.5. Again, what we've used is that z is x minus mu over sigma. We've calculated the number of standard deviations we are away from the mean. So we take away the mean and we divide by the standard deviation. So if I have probability of being less than 1.5, go to my table. I see 1.50 happens to be 0.9332. So we get 0.9332. In a similar fashion, I could do the one with greater than. I have to first convert it to a z-score by taking away the mean and dividing by the standard deviation, which is the probability then that z is bigger than minus 1.2 over 3, which is a probability that z is bigger than minus 0.4, which again, now remember we have a greater than. That's 1 minus the probability that z is less than negative 0.4, which is 1 minus, let's look it up on our table, negative 0.40 is 0.3446. So I get 1 minus 0.3446, which is 0.6554. Okay. So again, if I give you a mean and a standard deviation, I can convert it to something I use in the table by using this formula that gives me the z-score given any mean and any standard deviation. And it doesn't matter if I'm using the mean of the population, and the standard deviation of the population, or the mean of the sample and the standard deviation of the sample. I still go through the same process. I want to find the number of standard deviations I am away from the mean to get a z-score, and I'll look that z-score up in a table. So let's take an example where we did between. So this would be the probability that 17 minus 20 over 3 is less than z is less than 21 minus 20 over 3. I'll have to convert both values to a z-score. So I end up with minus 3 over 3 is less than z is less than 1/3. In a fraction, or in decimal, that's minus 1 is less than z is less than 0.33. In order to use the table, I will have to round this to 2 decimal places. So in the table, I would get the probability that z is less than 0.33 minus the probability that z is less than -1. So we can go to our table, and I'll get 0.33 has a probability of 0.6293. And I'll subtract off then the value that goes with -1, which is 0.1587. So we get 0.6293 minus 0.1587, which is 0.4706. Well, that should give you some examples to work in finding probabilities. What if I want to go backward now and find a z-score? So, for example, let's find the z-score that corresponds to the 80th percentile. Well, in our previous examples, we started with a score where we looked down the column and across the top row and found something from the body of the table. And that gave us a percent value. Well, in this type of question, I want to work backwards. I've told you what to look for in the body of the table, and I want to find the z-score that goes with it. So I want to try to find the value in the body of this table as close to 0.8 as I can get it. Well, the best that I can hope to do is 0.7955. So that's about my 80th percentile, and it happens at a z-score of, let's see, 0.84. So we know that a z-score, the probability that z is less than 0.84 is approximately 0.80. Let's say we want to find the 92nd percentile of z. Well, we'll go to our table, we'll look up 0.92, as close as we can get to it. So we're going to look for as close as we can get to 0.92. Notice that there are 2 values that are about equidistant away. So since these are about the same distance from 0.92, I'm going to say that the z-score that goes with it is about halfway between these 2 values. So we're going to use the 1.4 row and we're going to take halfway between 0.00 and 0.01. So we would say its Z is 1.405. So we would say a z-score of 1.405. So in other words, the probability that z is less than 1.405 is approximately 0.92. Well, let's kind of put that in context now with one final example. Let's suppose that my mean is 50 and my standard deviation is 10. Let's find the x value. So suppose x follows a distribution with that mean and standard deviation. I want to find the x value that corresponds to the 90th percentile for x. Well, the first step is find z such that the probability of z being less than little z is 0.9. In other words, I want to do like I just did with my other two examples, but look in the body of the table for 0.9. So I'm going to go in the body of the table and try to get as close to 0.9 as I can. And notice that that happens at right here. 0.8997 is as close as I can get. And that happens at 1.28. So that would give me that z is 1.28. So we figured out a z value of 1.28. So now the second step is solve x minus mu over sigma equals z for x. Or equivalently, x is equal to mu plus z sigma. So for this problem, x is 50 plus 1.28 times 10. All right, remember we had a mean of 50 and a standard deviation of 10. So that would give me 62.8. And again, if I have to do something where I need to repeat this test and I don't want to come up with percentiles all the time, I just have a threshold that needs to be met. This gives me a way of calculating that. So now, once I pull the value out, I can see what the measurement is. I know if it fits the specifications that I need. So let's say I was doing something where I was I have a one-size-fits-all garment, and that it really is set to fit 90% of the population. So anybody that's has a size bigger than this would be out. You'll see other context and some examples of where this might come in. Again, the one that we used earlier was with like diabetes, to where if the blood sugar is above a certain point, we're going to classify you as diabetic. We would like to know what that point is, and we can use information we have from measuring from the population to say this is what normal blood sugar is, and exceeding a certain level would be considered high blood sugar. So that concludes the examples for this section.